I'm going to use a free program called Audacity to generate 4 tones for you, and those 4 tones hopefully are going to teach us a few things about waves. Okay, so here we go. I'm going to generate a tone, and the default that it wants to make says the frequency is 440. Frequency is how many waves it makes per second, so it's going to make 440 waves per second. I'll play that for you in a minute here. And the amplitude is going to be 0.8. The amplitude tells us how much energy or how loud the sound is going to be. So let me generate that, and then I'll click play. So that's 440 hertz with an amplitude of 0.8. Now I want to generate another tone, and this time I'm going to cut the amplitude in half. So it's going to be 0.4. So this wave, you can see the blue bar across here is a lot shorter, or skinnier, I guess. Let me play that one. Oh wait, I gotta mute the first one. So let me play the second one. Okay, it sounds just like the first one, except it's quieter. Okay, so let me, I guess I'll mute both of these two. And then what I'm going to do next, I'm going to generate another tone, and this time I'm going to go back to my original 0.8 amplitude, but this time I'm going to mess with the frequency. I'm going to have more waves per second. So let me play this one for you. Okay, so a higher frequency means a higher pitch. All right, now let me generate one last tone. Oh, no, I don't want to do it in the same place. I want to do it down here. And this last tone is going to have a frequency of 880, and I'm going to do the same thing I did before. I'm going to cut the amplitude in half to 0.4. So let me mute this one and then play this last one. It's the same as the other one, it's just quieter. Okay, so just because I'm curious, what happens if I unmute them all and play them all? Okay, some weird stuff's going on there that we don't need to talk about. Okay, now, what can I do with Audacity that makes this worth my while? I'm just generating sounds. Well, watch this. I'm going to zoom in on these. And as I zoom in, you're going to notice that you can start to see something that you might recognize. I see this wavy kind of a shape here. And let me bring in an image here with the program I normally use to do this. And I took a screenshot, and here it is. So these waves that I've just generated are right here. How are they different from each other? Well, that's what I'm doing this video for. Now, the first one that I made had an amplitude of 0.8, right? And so that is how tall the wave is. So that's how big it is. Or you could go from the 0 line down to the bottom. So that height right there, the height of the wave, is called the amplitude. You'll notice that the second wave that I did looks quite similar, except the amplitude is shorter. So this one has more energy, and this one down here has less energy. All right, even though they have the same frequency. Now let's look at something else. There's a crest here and a crest here. The distance from crest to crest is the wavelength. And you'll notice that these two waves have the same wavelength. That's why they had the same sound. The only reason that the bottom one was quieter is because it had less amplitude. Okay. The second thing that I messed with, or the third wave that I created, was different from the first two. This one had a wavelength that was shorter. And rather than writing the word wavelength, I'm going to draw this Greek letter lambda. It's just a shorthand for wavelength. So the amplitude of the first wave and this wave are the same. They both had the same height. They had a 0.8 or whatever it was, and they had a different sound to them. The reason why is because this one had more waves per second. It had a higher frequency. So higher frequency kind of goes along with lower wavelength. So if you have a lower wavelength, you have a higher frequency. So deep bass would be really long waves, and high treble would be short waves. I hope you never hear me do that again. Okay, now the last wave that I made was shorter. That means it was quieter, so the amplitude was only from there to there, or if you wanted to measure it down here, it would be from there to there. And it had the same wavelength as the first one did. If I measured from, say, here to here, it would be the same thing as from there to there. So they have the same wavelength. Do they have the same energy? No. The taller one has more energy because it's got more amplitude. Okay, now one last thing. I want to finish this video, but I want to show you one last thing because there's something kind of inherently wrong here. These waves, these up and down kind of ripples, those are called transverse waves. And Audacity uses transverse waves to show us sound because it's kind of easier to represent on a computer screen. But sound waves are actually not transverse waves. They don't have these up and down ripples. Sound waves actually are kind of like this. Sound waves have particles shaking in a line back and forth. And the wave, you can see this dark region kind of going across here. That is how sound waves actually would look if we could see them. I found a different one on a different website, like this one. Like, imagine a speaker pulsing in and out, and as that speaker moves, it's hitting the air particles, and you can kind of watch these bunches of particles moving. It seems like they're moving all the way across the screen, but if you pick any one particle, you'll notice that all it's doing is shaking back and forth where it is. So just to kind of clarify any misconception, I wanted to let you know that sound waves don't actually have these down and up kind of things. They actually have the particles going side to side, but once again, Audacity uses these because these are easier to show on a computer screen and have people use them.